This is the last video for kinematics and calculus. We're looking at how to evaluate something called the definite integral. What the last two videos have been about is antiderivatives, or indefinite integrals. And we'll see where that name comes from in a second. But sometimes, you just need to know how far something went between two times. You don't need x of t as a function of time. The antiderivative gives us x of t as a function of time. But here's the kind of problem where we don't really need to know x of t as a function of time. We just need a number is the answer. And in this one, we've got the speed of a drag racer is given by the expression v of t equals 14t minus 2t squared. So the question is, how far does this drag racer go in the first 5 seconds? Once again, v of t is not a linear function of t, so we can't use the kinematic equations. We've got to use an indefinite integral. But if we want to know how far it goes in the first 5 seconds, what we have to do is get its position at 5 seconds minus its position at 0 seconds. So what we can do is perform the integral and then evaluate it at 5 and 0 and take the difference. The way we'll represent this as x of t equals the integral of v of t. But now we're going to introduce a little bit of additional notation. Delta x between 0 and 5 seconds is equal to the integral, and we'll put little numbers here. We call these the limits of integration. Meaning the start and end points that we're interested in. And then we will put 14t minus 2t squared dt. And sum rule says that this is equal to 14 times the integral from 0 to 5 of t dt minus 2 times the integral from 0 to 5 of t squared dt. Now the integral of t is just t squared over 2. And then minus 2 times the integral of t squared is t cubed over 3. But when we're doing a definite integral, we do not need to add the constant of integration because of what we're doing. We'll see that later. What we do need to do is indicate that we still need to evaluate this. This means we've done the integral, we have not plugged in the limits of integration yet. This expression in here is x of t, basically. Now we need to evaluate that at 5 seconds and also at 0 seconds. So evaluated at 5 seconds, we have 14 times 5 squared over 2 minus 2 times 5 cubed over 3. And we need to subtract that whole thing evaluated at 0. But we notice that both of these terms go to 0 when you plug in t equals 0. Come on, computer, stop lagging. There we go. And so that's just 0. At this point, we plug it into our calculators. When you work this out, you get 91.7 meters is your answer. That is how we use definite integrals. Your calculator can do definite integrals quite easily. For TI-83, it's pretty easy. For Casio, if any of you have a Casio, I have no idea how those work. But once you get a definite integral on a physics problem, feel free to plug it into your calculator. Unless, of course, it's on the multiple choice section where you don't get a calculator. But they're not going to give you any really difficult integrals in the multiple choice section. Now, you've done definite integrals last year. The indefinite was new, but you've already done definite integrals. Every time we said we were finding the area under the graph, we were doing a definite integral. So let's imagine that we have v is a function of time. Looks something like that. Just making something up. You know that velocity times time is going to give you some kind of displacement. So let's look at what happens in a very short length of time dt. Now that's v at t. If we look at this quantity, v times dt, that is going to be the area of that little strip of the graph. And that tells us the very small displacement that occurs during the time interval dt. So that's the importance and the physical interpretation of that variable of integration dt, and it's why you shouldn't leave it off. So v of dt is the displacement during dt. If you want to find, let's say, the displacement between t1 and t2, what you have to do is break this area up into a bunch of little strips and add them all up. And so you do what we call a Riemann sum. You may have seen this before, where you do the sum of v of t times dt, summed from t1 to t2. I'm being kind of sloppy with the math notation here, but the idea is that we're summing up all those areas. Well, as dt gets closer and closer to 0, this just becomes an integral. The integral of t1 to t2 of v of t dt. So if you have a graph of a function v, you don't actually necessarily need to use an antiderivative to find the area. You could just find the area the way you did last year by counting the squares or doing some geometry or something like that. Problem 13 in your physics textbook is an example of a definite integral that can be performed without using an antiderivative. For tomorrow, at this point you should be able to do all the antiderivative problems. Please work them by hand first and then check your work with the calculator. Don't just put it into your calculator the first time. I want you to become comfortable with this so you can do it without a calculator, and then you'll understand what the calculator is doing and you'll be able to use it more intelligently.